All right. We'll quickly go through what we were looking at in the last class on Thursday. We took a nonlinear equation, and this once again happens to be my favorite spring mass system, except that it's a non-linear spring, and this y double prime equal to minus y cube plus 4y is something which is a nonlinear equation, and whatever methodologies that we have seen in the past are going to have trouble. And therefore what we said was that we would still like to stay in the linear domain and convert it into some kind of a linear system. And the methodology we have already seen, and you get some kind of a Jacobian matrix, and you do a little bit of algebra, and what you get is the matrix or the linear system is going to be what is given on the right hand top bottom here. And this is what is going to be the linearized version of the equation. And of course, the solutions are going to be valid only about these so-called equilibrium points. Okay? And remember that when we had obtained these equations, this y is indeed y minus 1 yp and v minus vp, which is the so-called equilibrium point. And therefore, this y and v becoming equal to 0 is going to be a situation where the system is not going to be doing anything once it reaches that point. Okay? But once again, this is the linearized form, which means that whatever we are solving is going to be valid only in the vicinity of that solution and nowhere else, the vicinity of that point. Other places, linearization is not valid, may be valid, you may be able to make some guesses, but in general it is not going to be valid. So this guy has got two roots, and if you look at the eigenvalues are plus and minus 2, and the eigenvectors are going to be equal to that. Okay, so we had two imaginary eigenvalues, which means that this is plus minus root 8I, which means that there are going to be two so-called center points, and those 2 points are what you see as those little circles there. And the last point, which is y equal to 0, v equal to 0, once you go ahead and look at the eigenvalues and eigenvectors, you see that you've got one positive and one negative eigenvalue, which means that it's a saddle point. So saddle point means that's what's going to be the behavior of the solution, and we have said that this is the point about which the solution is valid. And there are these online tools which are available, but then you must understand that those online tools are going to solve the entire nonlinear system, and in this particular analysis that we have done, we are getting only the solution for the linear system, which means that I am going to be interested only in the regions where the linearity is going to hold. I'm not interested in the other regions, and if a question of that nature should come on the exam, I don't expect you to simply just copy down whatever is coming from the online source, but you need to be able to sift what is it that is being asked. All right, and then we said that there is some physical meaning to this, because this is a spring mass system, nonlinear spring. So there are these points, those valleys that you see here are those solutions for the imaginary eigenvectors and eigenvalues. So this is one point, this is one point, which was root 2i and minus root 2i. And if you want to think about this as some system where you have some kind of a shape like that, and you have a ball there and you want to drop the ball, you take this ball which is here and then you take it little bit away and then you leave it, the ball will just keep on going to be oscillating there. Okay, or if I want to think of a spring and a mass, and if you leave the mass, perturb the mass, it will just keep on oscillating ad infinitum in that location. Whereas if you are in this region here, this is the saddle point. This was something that we did not get when we were talking about the linear spring. That saddle point is an unstable point, if you will. So at that particular point, everything is fine, but the moment you are going to perturb it, you have seen that when you have that saddle, that plus lambda is going to take over, and then it's just going to push you away. Where it pushes you, I don't know, but it could take you here if this were the actual profile that we were talking about. Okay. All right. So then we said that this is about all we are going to say as far as the systems of equations are concerned. And then we started looking at something tangential. At least it looks tangential, but actually it is not. Okay, so one more example we looked at, and that is something which I said that you can go ahead and work out the details. All the required steps are in here. This just gives you a little bit of practice, and we are going to be uploading one last assignment on phase portraits and stuff like this, but there is going to be no submission for that. It's just your own interest to go ahead and work them out. And like I had said, up to and including whatever is this particular example is going to be showing up on the midsem. Okay, or questions related to that will be showing up on the midsem. Okay. Then we said, okay, now let us go ahead and look at something else. And we started looking at something called the vector space. And vector space is not what we are interested in, but it's just a kind of warm-up exercise to get to where we want. We said that some common stuff about vector space. Once again, your math instructor must have done a much more thorough job of this. But as an engineer, I'm interested in some things that permit me to get by. I don't know very much about this myself, but your math instructor is the best person. But we just did some hand waving so that we understand what this vector space is. So what we said is that the vector space has got vectors and a set of scalars, and the sum of any two vectors is going to be part of that vector space. Similarly, a vector that is multiplied by a scalar is also part of that vector space, and you can have real vector space, complex vector space, etc. All that is preliminary stuff. Then what we said was that the smallest number of vectors required to define a vector in a vector space is the basis. Okay, this is something that we need to keep in our mind. So if we have got a two-dimensional vector space, then you need two vectors or the two basis vectors, and the dimension of the vector space is the number of vectors in the basis set. All right, then couple of trivial definitions, if you will. The norm of a vector is the square root of the transpose of the vector times the vector under root. And if you have got any two vectors v and w, the angle between them is going to be the dot product of the two divided by their respective magnitudes. And the reason why we are interested in the angle between the two vectors is because we want to talk about what are called orthogonal vectors. And if two vectors are orthogonal, then the dot product for the two vectors is going to become equal to 0. And two vectors are orthonormal if the magnitude of each of these vectors is also unity. You can make the magnitude unity just by taking the vector and dividing it with the magnitude of the vector itself. Okay, then we said there is something called an orthonormal basis, and if you are having a set of basis vectors and they are orthogonal to each other and the dot product is going to be equal to unity with respect to each other, then that's an orthonormal basis. Okay. So so that's where we were when we quit last time. Today we'll take a small digression, and I'll quickly go through the solution for the exam that went by. The solution is already posted on Moodle along with your marks, and you can take your answer books back at the end of class. I'm going to stop 5 minutes early today, and the last 5 minutes I will use to distribute your answer books. And you're welcome to ask questions on queries. I do make lots of mistakes, correction, but you are welcome to tell that, okay, I have not been given credit for so and so, so and so. That's why the solution is also posted up there. And there's no big hurry on that. You can do that up to the next exam. Okay, so till the next exam, you are welcome to think about the solution, look at the solution, do whatever, and we will entertain queries on the these things. Okay, so I'll just quickly go through the solutions for this. They're already there on the Moodle, but just some couple of comments is what all that I'm going to be doing before we move on to the material. Okay, the exam was graded for a maximum mark of 30, and the high in class was 30 and the low was 6 or something, and the average was 17. Okay, so from a stats point of view, it's quite all right, but anybody who has a mark less than the average needs to be a little bit concerned. And if you have less than 10, then you need to be really, really concerned. Okay. There were several people who had the 30, some 4 or 5 at least. So it was a fairly straightforward exam, not too difficult, but then the material itself is such that we can't ask you very difficult questions. And many of you have seen many of these things before. Okay, so the question number 1 was something which was a giveaway actually, and many of you cashed in on it, but there were still a few who did not get it right, which is surprising because this is just basic calculus that was being expected. And such questions will be there on the midsem also. These type of questions are there so that people feel good about the fact that certain things have been answered completely, and till the end everything is correct. Okay. And nothing very difficult about it, both in terms of understanding or in terms of the algebra, but some amount of effort has to be put, and that was what was given there. U prime equal to p of x u square plus q of x u plus r of x. Check for linearity. That was the first question that was asked. And One thing that you need to understand is that when you have this type of thing, u prime equal to px u square plus qx u plus r of x. When you are looking for linearity, you are only looking at that part. You are not looking at the non-homogeneous part. Okay. I have not deducted any marks for this because there are any number of you who are taking this along, and then you are saying that, which is very nicely done by many of you. You have said that, okay, u1 is a solution, u2 is a solution, sum of the solutions or a linear combination must satisfy it. But then when you do that, you will find that this guy is going to show up 2 times, and then you get into trouble. Okay. Then you wave your hands and just say that, okay, it is linear. Okay. But remember that this is the operator, and this one is not taken. This one is taken to be equal to 0 when you are talking about linearity or otherwise of a system. Okay. We are going to come back to this linear system again. It's the operator that we are really talking about, and this fellow, if it is linear, then whatever is inside here, we keep it equal to 0, and then you go ahead and do this, and you do whatever is given there, and you are going to be able to show whether it is linear or not. Straightforward, but if you put the r in there, then you get into trouble. But I have just closed my eyes to that for those who have done it, but in future I'm not going to close my eyes. Okay, then a transformation was given, and u equal to minus v prime by p times v, and all that was being expected from you was some amount of brute force algebra and nothing else. Okay. You were just supposed to do high school calculus, but a little bit in the meticulous fashion, and already you have identified that square term is there, which is going to give you trouble because we have not worked anything out with non-linear except in the last one class or so. There also we have linearized some things. So this was something that you were supposed to do, and at least realize that that square fellow is going to go away once the algebra is done. I'm not saying everybody has done that. 80% of you have done everything correctly, done the algebra also quite all right, and then you have said that there is going to be the transformation is useful for you because it's transforming that equation into some kind of a linear system, which you can now go ahead and solve by whatever means that are available to you. Okay, so question number 1, by and large, the entire class had no trouble with it. That's why at least if somebody has an average or somebody has a score less than 10, you need to be really concerned. Okay. That's why we also expected the average to be of the order of 20 plus. But surprisingly, even this question, there were quite a few of you who were wanting as far as the solution was concerned. This was not as straightforward as the question number 1, but still fairly straightforward. A question exactly of this nature, which was this, was worked out in class. There were several like this, which were home assignments, and therefore just there was one more of this, and everybody claims that they have done their assignments on their own, but I don't see why so many of you had trouble with that question. Okay. So you were asked to use the Heaviside function and go ahead and get a solution, and when you are asked to do something, please do it. Okay. There were still a few, not very many, you could count them, but there were still a few who want to go ahead and get the solution, and then you say that, okay, this part of the solution, this part, you don't get the matching conditions correctly, even though this in class was done with all the methods, but you were asked to use the Heaviside function. And many of you did not put the Heaviside function correctly also. So you were penalized some 3 marks or something for not putting the Heaviside function correctly. So everybody is going up to here correctly, and then you should realize that this guy is not there, and I want another auxiliary Heaviside function which is going to cancel that guy off. Okay, so that's what the second term is, t minus 5 by 5. This is this guy here, right? But then this guy here is going to be there only till t equal to 10. Okay, and then this guy has to be killed. So you need to have a Heaviside. This Heaviside already is there, so another Heaviside on this other direction, so that this plus this is going to kill that the one that is moving up. So this guy had to be killed right there. So that's why you have a ht minus 5 minus an ht minus 10, and many of you have just not used this here, and I have remarked on your papers that whenever you are trying to represent a function, you put the numbers back and check for yourself whether you are getting the function back or not. Okay, so if you are not getting the function back, it means that you need to do something else. Okay, so the same thing was true for this also. Many of you have not used this part here. So this guy here is coming down, but then if you don't use the other part, this guy keeps going down. So you need the other guy who is going to go like that, and then this plus this is going to get cancelled off, and finally you are going to get the proper Heaviside, the function that is being asked for. Okay. And there are still a few die-hard fans who are actually performing the integration and the Laplace transform. It's not worth it, because you do that, you spend a lot of time. At the end, you sometimes get the right answer, sometimes not. So that's where the online tools have been given to you, and you are going to use, or you are advised to use those tools. The purpose of this particular class is not to see whether you can compute the Laplace transform. It is to see whether you are able to use the Laplace transform to get a solution to something else. Okay, so that in an earlier math class you have done a lot of algebra, partial fractions, etc., etc. We have also done that in class in some sense, to some small extent, because we should not just go ahead and think that the online resource can do everything for you. Many times it can do some things it cannot do. Okay, so it's in your own interest to know everything, but at the same time, when required, use what is going to make life easy for you. And some of you have used this other approach, which is also fine. So you directly use the Laplace transform and then went into the integral form of the solution by using the convolution integral, which is perfectly fine. So whichever methodology you use, there is absolutely no problem. You are going to be ending up with the final answer. I usually don't see. If you are correct up to the last point, and then you say that you have used whatever tool to get the inverse. Inverse is a pretty bearish looking thing, so I'm not even sure what I have there is absolutely correct, but if you come up to that point, I give you full marks. Okay. So the intention is not whether you can go ahead and do a lot of algebra, but do enough algebra to go ahead and navigate through the question. Okay, the last question was the one where most of you had trouble, which was this question here, and it was kind of done in class in some sense, although not in exactly that fashion. So you were told that the solution was available for that system. Many of you have said that that's the homogeneous solution. It's not. Okay, so the equation is given to you the boundary conditions are given to you or the initial conditions are given to you and the solution is given to you, that's not the homogeneous solution, even though the right hand side is 0. Okay. So this cannot be the homogeneous solution. So x double prime equal to 0, just because there is a 0 here does not necessarily mean that the x that has been given to you is the homogeneous solution. Okay. The conditions were already imposed in here. So x0 equal to 0, x prime 0 equal to 2. This condition, when you have imposed these initial conditions, you have got a solution. X was what was given to you, and that's not the homogeneous solution, number one. Number two is that many of you, what you have done is, you have seen the other guy who was y double prime plus, okay, so y double prime plus a times y prime plus b times y was equal to sine square of t, but the y0 was 0 and the y prime 0 was given equal to 5. And many of you just said, okay, this guy is looking like 5, this guy is looking like a 2, and therefore 2 by 5 of this happens to be the homogeneous solution. Okay. It's not entirely wrong. It's not entirely wrong, but it cannot be the homogeneous solution. Okay, so what you can see is, or 5 by 2 or 2 by 5, you can see the final solution that has been given. So you can just go ahead and perform this exercise, and you see that this guy is coming as an added baggage to the final solution. But that does not mean that this is the homogeneous solution. This is not the homogeneous solution, this is not the particular solution. Okay. This is some kind of a modified homogeneous solution, if you want to call it that, but and that is some kind of a particular solution, if you want to call it that, but strictly speaking, this is not the homogeneous solution. You cannot just say lambda e to the lambda t, etc., and then that solution happens to be this. Okay. Remember, there are no unknown constants here. Okay. So the homogeneous solution must have those two unknown constants. So you cannot get the homogeneous solution. That's what we have said so many times, that the initial or the boundary conditions have to be put after the final solution is obtained, when you are using the complementary function plus particular integral type of a solution. In here, the initial conditions, when you use the Laplace transform approach, the initial or the boundary conditions are inbuilt into the process itself. Okay. So there's nothing like a homogeneous solution, or although you may think of some things in that particular fashion. So this was the question where people had a lot of trouble, which is why the average came down to this number. But apart from that, I think this question where people had a lot of trouble, and then the question on the heavy side where many of you did it right, some of you had trouble. Question number 1 was where none of you should have had trouble, some of you did have trouble on that also. Okay. So the midsum is going to be similar. There are going to be some lollipop questions like that. I don't know if any of you know what is a lollipop, but nevertheless, when we were kids, lollipops were very, that's all we could afford. And nowadays you have all these Hershey's and all that. Okay, so those are easy questions which you are going to be able to take care of. Okay, so something like 50% of the question paper is given so that people can score marks. Okay, is the other 50% which will be slightly difficult, which requires some amount of understanding on your part. So our midsem, I think, is a week from tomorrow. The institute has given some timetable, etc. And what we have said is that everything, and including the system of equations except the function spaces that we have started, is going to be showing up on the midsem. Okay, anybody have any general questions either on this exam or on the midsem that is going to follow. Yeah. Yeah, I know. He also told me for some reason I have been little bit sloppy in uploading the slides. I will do that. Okay, anything else? Up to, that's what I said. Up to, I will not even talk about topics. Up to this particular February 13th slide number 1. That's the last one that is going to be what you are accountable for on your midsem exam. Okay. Although I think this, the reason why I have not been uploading is because for some strange reason 2, 3, 4 classes are getting combined because the speed is changing and things like that. But nothing of this business is going to be showing up on the exam. Everything after this, including this slide that we are talked about, is not part of the exam. Okay, we'll stop about 5 minutes earlier today. I have set my alarm for that. And then I'm going to distribute your answer books back. So please give that attendance sheet to me back, whoever has it last, so that I just will announce the names of those so that it's much faster for me to give your answer books back. Okay. All right. So the last that we talked about was these vector spaces. And in 1 minute, we'll see why we have been talking about the vector spaces. So what we said was, how many of you thought the exam was difficult? Nobody? Great. I won't ask anything else. Okay. So we said that the vector which is there, we can usually decompose it into its components. Okay, that's the way we write a vector. So the vector v is going to be a times some kind of a unit vector. In the 2D space, I have got this equal to a times n1 times b times n2. Now, so far we have done some trivialities. So now let us see, or let us try to give some kind of a formal meaning to what this A is and what this B is. So what is this A? And what is the relation between this A and this V? I've got this vector V. We have said that there are some things called inner products, vector dot product. So V dotted with I, which let us say is N1. Let us just say this is I and this is J. What is V dotted with I? A. Okay. So this guy, and what did we say about V dot I? We said that V dot I is going to be the component of this vector on the I vector, right? So A is the component of this V vector on this unit basis vector, which is I. Similarly, therefore, what would be B? B would be the component in the J direction, or the vector product of the vector V with J. Okay. All right. So let us now say that I've got a general vector which is 3, 4, 5. Just some random vector that has been chosen. This is 3, 4, 5. Okay. This now we are going to write it as 3 times 1, 0, 0 plus 4 times 0, 1, 0 plus 5 times 0, 0, 1. So what is this 3 here? The component in the I direction. But the way I would like to now think about this is the vector product of the dot product of the vector v with the I vector. Okay, right? So this is the projection of the original vector in this I direction. I project this original vector in the I direction. Similarly, and then what do? I project this vector in the I direction and multiply it with that same vector. Right? So this is the projection, this is the multiplication. And we have said that this is going to be a definition. Dot product is just a definition. So the definition of my dot product is V transpose V. This is what we have said is the definition of my dot product. So this guy is V transpose times whatever is this I vector. Okay. All right. So what we therefore have is, I have got the projection of this vector along this I direction plus the projection of this vector along this direction, projection of this vector along that direction. All this is trivial stuff that you all know. Now let us go and say that we will extend this same definition to a function space. We have talked about a vector space. Now we talk about a function space. Okay. So the function space, in the function space, I have any function f. How would I represent any function f in the function space? Go to that definition there. Okay. Is the projection of this function along a basis vector times the basis vector. Okay. So I don't know what these basis vectors are yet, but that's a hypothesis that we are going to put forward. And what's the projection? In that case, what was the projection? The projection was the inner product, the dot product of that vector with the basis vector, right? So now we say that the projection is going to be the inner product of this function f with a basis function. Just a parallel definition that we are using. We still don't know what this definition is though. Okay. What is the inner product? Now this dot product is something that we have been using. We are now going to call it an inner product. Dot product and inner product are the same things. So for a vector, we said that the dot product is V transpose V. Just a definition that was given to us. So let us define the inner product for a function. Okay. So now we have got a function space. So just like we had a vector space, we have now a function space. That's why we spent so much time on a vector space, even though we know everything about the vector space. So there is a function space, and now just like we had those 3D or 2D vectors, we are going to talk about functions which are 2 pi periodic functions. Okay. The function space of 2 pi periodic functions. So we are talking now of a function space. So in that vector space, we had those Euclidean vectors I, j, k, etc., which we all know. Now this is a function space, which is a huge space, and a subset of that is the function space of 2 pi periodic functions. And then the same definitions that we had are going to be there. The multiplication of a function with a scalar is going to be part of that function space. If you add up two functions, the new function is going to be part of the function space. All the same definitions that we had in the vectors space are going to be here also. Now, what is the inner product? So we now say that there is something called an inner product, and we are going to define this inner product now between two functions. So the inner product of two functions f and g, we are going to use these square brackets or whatever angle brackets, and say that this is going to be equal to 1 by pi integral minus pi to pi f g dx. This is my definition for my function space, inner product. Okay, so I've got an inner product and I have got 2 pi periodic functions. I can put forward a definition for the inner product for the functions, and that's the definition that we are putting forward. The inner product of two functions f and g is 1 by pi minus pi to pi f g dx. Okay. Then, just like in our vector space, we need to be able to represent any function that we have in that 2 pi periodic space. So what we said was, we are going to take the projection of that function onto a particular basis function. So which means that I need to now identify the basis functions in this 2 pi periodic function space. Okay. So what are the basis functions in this 2 pi periodic space? Okay. So what did we say are basis functions for our 2D vector space? What were our basis functions? What were the basis functions that we had? I and j, right? That was for that. And what was the property of those functions? They were orthonormal. We had orthonormal basis. This is a convenience for us. So we had orthonormal basis functions. We are going to use the same definition here. We are going to say that we are going to choose orthonormal basis functions. Okay. Now what was orthogonality? Orthogonality means, for the two vectors we said that orthogonal vectors means they are perpendicular to each other, right? So what does orthogonality here mean? Okay, so orthogonality of two functions was V transpose V equal to what? Vectors. V transpose V equal to, if you have got two vectors that are orthogonal to each other, V transpose W equal to what? 0, if they are orthogonal to each other, right? So similarly, this we are saying is the definition of my inner product. So therefore, my definition of inner product here was equal to this. This was my definition for my inner product. So if I have got two functions which are orthogonal, then what should happen? This integral should go to 0, right? So this is going to be equal to 0 if the two functions are orthogonal to each other. Now what does orthogonality mean for functions? I have no idea. Okay. So for a vector we know, okay, they are perpendicular to each other. For functions, I don't know. But I don't care either, because I've got a definition which says the inner product is defined like this. And in the domain of this particular definition that I have, orthogonal functions are those for which 1 by pi minus pi to pi f g dx equal to 0. That's my definition. Okay, what about normal functions? So we said that these are orthonormal, right? So if a function has to have a unit magnitude, then what did we say about V transpose V? If the function is of unit magnitude, then the vector sorry, if a vector has unit magnitude, what has to be V transpose V? 1. Okay. So similarly, what we will say is that the inner product of a function with itself should be equal to unity if it is a function which has got a value equal to 1. Right? So an orthonormal function, orthonormal basis function will have inner product with itself f comma f is going to be equal to 1 and f comma g is going to be equal to 0. This is going to be an orthonormal function set. So any function which is 2 pi periodic, we are talking only about 2 pi periodic functions. Okay. So any function that is 2 pi periodic, and if we are looking for an orthonormal basis of this 2 pi periodic function space, this is the definition, is f comma f equal to 1, f comma g equal to 0. Okay. So that is going to form an orthonormal basis set. Okay. Now trigonometry has given us some very nice functions which are orthogonal, and if we look at sines and cosines, so sine mx, now let us say I have got sine mx sine nx, inner product. What is this equal to? Sine mx sine nx dx from your trig course. Integral of sine mx sine nx minus pi to pi, 0, right? So this is 0. I am not showing this or proving this. I am going to show it later on when it is much easier for me. Here it is slightly more difficult, so I am just going to say that you look at your trig identity and you know that this is going to be equal to 0. Okay. And what about sine mx with itself? What is that? 1. Okay. So your trig identity has told you that cos mx cos nx sin mx sin nx integral is going to be equal to 0 if m not equal to n. If m equal to n, it is equal to 1. Okay. Now what do you mean by these two functions being orthogonal? I don't know, and I am not so concerned about it either. Sin mx, sin nx, cos mx, cos nx are all orthogonal functions. All orthogonal, and if you are going to take the inner product with themselves, they are unity, and so this is an orthonormal basis. Okay. So now these are sines and cosines. I would like to have a scalar also. Okay. So what is the scalar that is going to be satisfying this business of orthonormality? Suppose I have got 1. Okay. So now what we have established is all sine mx sine nx, right? So sine of nx cos of nx. Okay. All kinds of sines, all kinds of cosines, they are all forming a basis, right? A set of basis functions, because the inner product when m equal to n is going to be equal to 1, when m not equal to n, it is equal to 0. What about this guy called 1? So if I try to find out the inner product of 1 with 1 and I use the definition minus pi to pi 1 1 dx, this comes out as equal to what? Okay, we stop here for today.